Disclaimer: this video contains jokes for comedic purposes. It's intended to be a more accessible version of the information provided in the scientific paper explaining the whole process behind creating the project. All of the science behind calculations, necessary equipment, and all other academic requirements are explained in greater detail in the paper. The explanations in the video are more surface level, and everything you see is done under professional supervision in a professional environment. If you plan to replicate any of the experiments, please take all the safety precautions. Thank you for understanding and enjoy the watch.
Woo! Science Fair 2025! Anyways, the topic of today's video is ZIF-8 Meta-Organic Framework, Experimental Synthesis, Characterization, and RASPA-driven CO2 Adsorption Analysis. Basically, we're experimentally synthesizing a meta-organic framework from scratch. We'll get to what this means in a moment and provide certain characteristics of the MOF, short for meta-organic framework, as well as adsorption of CO2 data we have acquired through quantum simulations on RASP. And now we'll be moving on to the
Abstract. We'll explore the synthesis of a MOF in a non-specialized laboratory setting. The main objective is to outline the steps required for MOF synthesis while identifying and addressing potential challenges that will arise in the multi-step process. The selected MOF for this investigation is ZIF-8, zeolitic imidazole framework 8, a material gaining significant attention for applications such as adsorption, chemical sensing, gas separation, photocatalysis, electrocatalysis, and catalysis. Rather than following a single protocol, the synthesis process was developed through the investigation of multiple scientific papers, combined with creativity, experience, and experimentation by the researchers. The methodology includes the synthesis of acetaldehyde as a precursor, the subsequent conversion of acetaldehyde to galeoxyl, the formation of 2-methylimidazole from galeoxyl and acetaldehyde to surface the organic linker, and finally, microwave-assisted synthesis for ZIF-8, and using 2-methylimidazole and zinc nitride. The scientific contribution of this paper does not lie in the final compound itself, since ZIF-8 is a well-researched MOF, but rather in demonstrating a feasible synthesis approach using accessible reactants and without advanced laboratory equipment. Along with the synthesis process, the paper also contains a computational chemistry part which outlines the relationship between the pressure, temperature, and the absorption of CO2 in a ZIF-8 compound. The values were acquired using 40 simulations in RASP-2.
Introduction to the chemistry and physics of meta-organic frameworks. Let's begin with explaining what even MOFs are, because it ain't an easy topic. In the simplest way put, it is a fancy polymer with pores. The atoms arrange themselves like a crystal and create openings. And if you want to smash gases in there, you could. And if you want to catalyze reactions from there, you could. It just depends for what purpose you want to use them. Just a quick note, the majority of the information here is referenced from Daniel Rickson's PhD dissertation on functionalized meta-organic frameworks. So big thanks to that. Starting with the definition, a MOF is a class of crystalline polymer formed from the well-established principles of coordination chemistry. Their main characteristic is their high surface areas and porosity, as we already mentioned. MOFs are classified as coordination networks, which for those of you who don't know is a compound that repeats through coordination entities in one of the three dimensions, while in the other two it has crosslinks between two or more individual chains, loops, spiral links, or coordination compounds, which extend through repetition, creating a seemingly endless structure. The main takeaway is that coordination networks are much more flexible than standard polymers, as they could expand more uniformly. The simplest composition of a MOF contains nodes and linkers. Nodes are metal centers, most commonly zinc, cobalt, or copper ions. The nodes are held together by linkers, which are typically organic compounds, and some examples are terephthalic acid, tetrahydroxyquinone, and 2-methylimidazole, which is the one we're going to use later. Keep in mind, it isn't as simple as connecting two Lego pieces, but the concept remains similar. There are also secondary building units, which is a whole another topic, but to learn more about them, check page 6 of the paper. Moving on, recent research has created post-synthetic modification protocols for modifying existing MOFs, but these methods aren't plausible without access to fancy equipment. But their point is to change something small in the structure in order to better suit the MOF for a certain task. To synthesize these amazing structures though, there are 6 main techniques. Firstly, there is solvothermal, which uses a fancy water bottle and cooks the solution inside for a couple of days at high pressure. It's basically a glorified pressure cooker. Next up is the evaporative crystallization method. In it, you just leave the solution to evaporate for a couple of months. Not the most ideal for our case, but it generally produces the best crystals. There's also the microwave-assisted synthesis, which is what we're going to be doing later. You just microwave the solution until it boils off and leaves the crystals at the bottom. It would usually only take up a couple of minutes, so it's optimal for us. There is also the electrochemical method. In it, you use electrolysis to create the MOF by adding the solution to a galvanic cell. Next up is the mechanochemical method. You take a plastic jar with metal beads inside and shake the solution for a couple of hours. And finally, the sonochemical method. You would play Bob Ross videos at high frequencies to create a calm framework. The only actual options are the microwave and the plastic jar, but let's go with the microwave as it is more controllable and generally produces better quality products. Keep in mind all of these processes work by adding energy in the system and evaporating the solvent used for creating the framework. Once you have created your MOF, you need to purify it, so we do what's called activation. Basically, we heat it up in a vacuum till everything polluting exits the compound. There are a couple of different ways you could improve the process. Check page 10 for more details. Then, to check the product, you can blast it with X-rays, use spectroscopy, do thermogravitic analysis, basically check the usability, and check the gas adsorption patterns. But finally, why even make this if it is so complicated? Because they're great, actually. They can be applied to solve the excess releases of gases into the atmosphere. They can also be used as catalysts and for sensing dangerous substances like explosive, or most recently, they have been used as methods for drug delivery, as some of them are non-harmful and biodegradable. MOFs have great potential, and we're going to try to use them to catch CO2 and maybe prove that it is possible for MOFs to be used as filters to catch harmful gases for the environment, and thus probably mitigate climate change. It is insane, yes, I agree, but it is possible in the long term. So knowing what MOFs are, let's synthesize.
Synthesis of acetaldehyde. Finally, it's time we prove we are chemists, capable of more than hypothetical talk, by presenting you with our 4 successful syntheses, specifying successful because of our overestimation of the capabilities of the lab. The process of synthesizing acetaldehyde, or ethyl acetate, was pretty straightforward and didn't require much research. What we basically did was go online, search up if it was possible to oxidate alcohol with atomic oxygen, and if it yielded ethyl acetate. And after confirming it was a plausible reaction, we decided we were capable enough to figure the rest on our own. We calculated the volumes and concentrations of the reactants through simple stoichiometry, remembered that the reaction is failed in an acidic environment, and prepared the experiment. In order to optimize the reaction conditions, we decided to keep the reaction mixture under constant stirring while adding the 60% ethanol and 15 more sulfuric acid at 300 rpm. While adding our chosen oxidizer, potassium permanganate dropwise, over a period of 5 to 10 minutes, we prevented the large amount of oxidizer to instantly oxidize any acetaldehyde molecules into ethanoic acid, which, we spoiler alert, still got. In order to isolate the desired projects from the reaction mixture, we did what any self-respecting chemist with a passion for engineering does. We construct a simple distillation setup and heated up the reaction mixture to around 70 degrees Celsius in order to boil the products, which had a boiling point of 20 degrees. Overall, we needed to conduct this reaction process more times than I can count, because we needed about 400 to 500 milliliters of acetaldehyde with an average success rate of about 40 to 60%, which, to be fair, was really good and a cost-effective process for the laboratory, as supplying that amount of acetaldehyde would have set us back about €100, as well as several weeks or even months of waiting for the product to arrive. Amazing! Now we have successfully completed level 1 reaction, and it's time to jump straight into the level 10 reaction by synthesizing glyoxal. Glyoxal is the simplest dialdehyde with 2 carbonyl groups on a 2-carbon chain. It is essential for the further synthesis of the reactions. Unfortunately, our glyoxal shipment got delayed by 3 months, so we decided to make it ourselves. We oxidized acetaldehyde using 30% nitric acid, which we found online that it was only a feasible process, which we safely carry out in the lab. We mixed 80 ml of acetaldehyde with nitric acid, stirred it at 300 rpm for 1 hour, and distilled the glyoxal at 70 degrees Celsius using the same distillation setup as last time. The reaction smelled like a mix of aldehydes and something vaguely unpleasant, but that's chemistry for you. Ask Navarrete if you need to. We collect about 40 ml with a yield of about 50%, which isn't bad for our DIY approach, as the information regarding the synthesis of glyoxal was highly limited or required conditions or chemicals we couldn't have access to. But of course the glyoxal we ordered online arrived last minute, so we had something to compare our product to, proving we indeed had something worthy of being called glyoxal. Next up was 2-methyl-imidazole, the organic linker we needed for ZIF 8. The only commercially available synthesis we found involves reacting glyoxal, acetaldehyde, and ammonia in a ratio of 1 to 1 to 2, which sounds simple enough, but as you've learned, nothing chemistry is ever simple as it seems. We mix glyoxal and acetaldehyde in a 1:1 mole ratio and add ammonium hydroxide dropwise while stirring at 300 rotations per minute. The solution turned from yellow to red to black, which is unexpected, but not entirely surprising given the complexity of the reaction and formation of side products. The reaction mechanism we theorized happened was that the carbonyl groups, where oxygen is connected to carbon atom through a double bond, of the two aldehydes interacted with ammonia in order to form three potential imines: ethanimine, ethan 1,2-diimine, and ethan 2-carbonyl, which interacted with one another, forming the intermediate on the screen. We heated it up to about 80 degrees Celsius for 2 hours to promote ring closure. Then we neutralized it and extracted the product with dichloromethane or DCM. The black solution was a bit alarming, but we didn't panic. Turns out some byproducts like pyrosines and amino acids were also formed, which is why I think the solution turned black. So, if any of you are still questioning the validity of our urine mirror experiment, we can kindly invite you and show you to the abomination. But hey, we've got our 2-methyl imidazole, so that's what matters. We use the separation funnel to transfer the methyl imidazole back to a water ethanol mixture and proceeded with the final synthesis. Finally, it was time for the main event, ZIF and the metal-organic framework we're working towards the entire school year. ZIF is made out of zinc ions and 2-methyl-imidazole ligands. And at least the paper, it was surprisingly easy to make. Foreshadowing, perhaps? We used a microwave-assisted synthesis method because it was fast and efficient, and honestly, it was the easiest specialized equipment we could acquire when we were initially researching the topic. We dissolved zinc nitrate, hexahydrate, and 2-methyl-imidazole in ethanol, combined the mixtures together, and zapped the solution in the microwave at 200 to 300 watts at intervals of 1 to 3 minutes, in several containers, including petri dishes and beakers. The solution rapidly concentrated and fumes started exiting the microwave after each cycle. We let it cool to room temperature and dried them under vacuum. The results were white wine crystals, exactly what we wanted, or at least what Google told us it's supposed to look like. The microwave-assisted synthesis was fast and efficient, and we got a decent yield of ZIF. Plus, using a microwave made the process feel almost like cooking, which was a nice change of pace. From acetaldehyde to ZIF, we've come a long way. Sure, there were a lot of hiccups along the way, looking at Liu black solution, but to prove that we are capable chemists who can do more than just talk about hypothetical reactions. Hey, we even saved some money in the process, but the world isn't full of unicorns and rainbows. Physics majors cry when air resistance is included in the calculations, and we, the chemists, cry whenever we realize we either don't have the fancy reactants we want, or whether the laboratory cannot handle the projects we want to tackle. As we're progressing with the project, we stumbled upon the idea of creating an antifungal antibiotic from the 2-methyl-imidazole, and the most promising looking one being metronidazole, with the proposed pathway being well documented in patents and relevant papers. We were sure it would be a piece of cake, but the conditions in the laboratory weren't on our side, and we avoided tackling the biological side of chemistry once again. Sometimes life doesn't go your way, and that's what happens when you shift your sorrow into motivation and start studying for AP exams, because they are right around the corner.
Computational chemistry. The process you see explained took 2 months in total because the only educated helper in the topic I had was my boy ChatGPT. And my boy kinda struggles with understanding the quantum simulation softwares I used. So I had to resort to reading hundreds of pages long documentation in order to understand how a software works. So here is the story of how we ran our own adsorption simulations, and it includes quotes from the journal I was keeping during. Long ago, the 4 nations lived together in harmony. Then everything changed when the Far Nation attacked. The initial plan was to use another simulation software and do totally different calculations. I wanted to use LAMPS and do molecular dynamics calculations, but the process just didn't seem to work. So much work was thrown out the window just because the software decided to break the whole structure, so we switched methods. It wasn't what I wanted to do initially, but I had no choice, so here's the summary of the successful process. Step 1. Create a Linux virtual machine. We used Kali, but you can use whatever you choose. Step 2. Install the software. As we have already said, we use RASPA. It specializes in calculating gas adsorption of frameworks, so it will be really good at finding out accurate values for ZIF. Perfect! Right? Wrong? As we again need to calculate the partial charges, but first we need a structure file. Finding a structure file. It turns out there are a lot of databases for acquiring these sorts of files, They're called .zif files, and they contain information about the framework's periodicity in space, which for MOFs is especially valuable. We use the Cambridge Structural Database, specifically this file you see on the screen. It's gorgeous, isn't it? And now we need to find the atom's partial charges. Now, how do we do that? Step 4. You don't... No, you do, but you don't. See, remember WAMPs and how it can calculate charges? Well, it can, if it wants. See, the program doesn't like me, sadly, and decides to break everything. Why? Because I'm dumb, mostly. Introducing PacMof! Yay! An AI trained specifically to predict partial charges of MOFs with DFT accuracy. Insane accuracy, by the way. So we just plug in the file and run the command. Oof, it still breaks. See, that's because I'm dumb. When you open the ZIF file and see the beautiful ordered messages, here it is written that it has cubic symmetry. And both WAMPs and PacMof use ACE, the atomic simulation environment, to convert the ZIF file to an XYZ file, which the programs can interpret. So to deal with this, we need to change its symmetry. Step 5. A new player has entered the chat. Vespa, my Lord and Savior. We input the ZIF file, and because the program is able to interpret cubic symmetry, we convert it into XYZ format. And then comes step 6. Back to ACE, using the simple script, we can convert it back to a ZIF file, but this time with triclinic symmetry. Step 7. Finally, when you have the triclinic file, you can input it into PacMof, and in literally 11 seconds it is complete. Yes, there may be more accurate methods, but the performance is still insane. Another reason why we didn't continue with WAMPs is that it just took weeks to calculate it using DFT, and it just wouldn't end, so we had to resort to PacMof. Step 8. Having the ZIF file with the charges ready, we can now use it to calculate the adsorption. Finally, after all these years, there is light at the end of the tunnel. Before doing that, let's just go over what RASPA would actually do. The algorithm used is called Monte Carlo. Familiar, right? Yeah, the financial algorithm Monte Carlo. It is basically the same. It turns out it can be used to calculate adsorption as well. It works on the same principle. It repeatedly samples until it reaches an accurate result. What it does is that it models the random interactions between gas molecules and the surface of a material by repeatedly sampling configuration and computing the corresponding energy states. The simulation estimates the equilibrium adsorption behavior and provides insights into adsorption isotherms and surface coverage. In other words, it tries thousands and thousands of times till it converges and the energy is minimized. Standard protocol for computational chemistry algorithms, as you already know. Based on that, we have chosen to do the following. We want to sketch out two dependencies, adsorption versus temperature and adsorption versus pressure. So we will do 20 calculations for each of the two at different temperatures and pressures and find the overall trend. The great thing is that RASPA doesn't require a lot of computational strength, but still an approximate of how much time the calculations will take is about 100 hours-ish total. We will need to set up the environment though, so step 9. Using this amazing script, we will create 20 copies of a directory that contains all of the needed items. Firstly, the input file. In it, we specify the framework we will be using, how many times the Monte Carlo algorithm is going to be run, the gas which is going to be adsorbed, the temperature and pressure at which the interactions are happening, and the helium void fraction which is specific for every molecule. And we found it online, and some other less important things are in the file as well. As well as the input file, you will need also the structure itself, the pseudo-atoms def, the force field mixing rules, and the force field def. All of these files were written by hand, by the way, and the information gathering took a lot of time. Anyways, having all of this, we make 20 copies of it, and then we manually change the temperature and the pressure in each input file. Afterwards, we call the input file, and the simulation starts. Having them line up in a queue from 273 Kelvin to 368 Kelvin, and from 0 pascals to 190,000 pascals. All we had to do was wait. Step 10. Transferring data. After all the 400 values are transferred, that took a lifetime, I'll admit, we are ready to construct some graphs and analyze them. Step 11. The end. The analysis. For real understanding, we deeply advise to check the paper as there are the full explanations for each graph. But here is the nutshell of it. First, the relationship between temperature and entropy. Slightly surprisingly, with the increase of temperature, entropy increases slightly and the reaction becomes less exothermic. This is because the reaction would not be favored at such high temperatures and because of these walls you see on the screen, but who cares about them? The adsorbent energy average shows how much the CO2 molecules interact with each other, and as expected, the higher the temperature, the more they interact, just because they emit more frequently due to high velocity. Finally, the most important part of it, the adsorption average. With the increase in temperature, adsorption plummeted down, more than we expected actually. In the span of 100 degrees, the change is insane. It is explainable though, through all of this, but with words, forming these bonds is not favorable at such high temperatures, so that's why we see that much of a change. Moving on to the pressure, the change of entropy with the increase of temperature is really weird. The explanation is the following. Keep in mind it is again in a nutshell. Entropy of sublimation is equal to the cohesive energy of the solid, right? So in the case of the simulation, the cohesive force will be the strength of the bonds between CO2 and the MOF, and the cohesive strength will decrease the higher the pressure. So essentially, less energy is required to break the bonds, but the formation of them releases the same amount. So in the end, the total energy of the adsorption will be smaller. That's why we witness an increase in the amount of energy released. We see a similar pattern for the adsorbent energy. It increases with an increase in pressure just because the molecules interact with each other. Finally, just bear with me for a sec, the adsorption average relationship with pressure is linear. What? And for other people it is too, what? Weird, right? Well, not really. It can be explained through Henry's law, but only for lower pressures like the ones we used. So that's it. To sum up real quick, ZIF 8 is great at capturing CO2. You can see more information in the paper, but at STP it can almost absorb 50 milliliters of CO2 per gram of it. And a great thing about these graphs is that there isn't information about the relationship between the absorption and temperature online. So let's wrap this video because it was quite the video.
Finally, it's time to move to the list of hypotheses and whether we confirm them. First one, the absorption energy and temperature. Adsorption is exothermic, so increasing temperature should reduce the energy released per mole, as the process becomes less favorable at higher temperatures. Results? The hypothesis was confirmed, but with larger inaccuracies than expected. The entropy change over 100 degrees was about 25%, statistically significant but negligible in real-world terms. Hypothesis 2. Van der Waals forces and temperature. These forces weaken with temperature, dropping sharply before plateauing at around 350 to 325 Kelvin. Results? Confirmed interactions followed a logarithmic decline with strong forces at low temperatures and stabilization at higher ones. Hypothesis number 3. Coulombic interactions and temperature. Similar to the Van der Waals trends, but scaled down as interactions depended on partial charges via Coulomb's law. Results? Confirmed. The changes were less pronounced compared to Van der Waals forces. Hypothesis number 4. Absolute adsorption and temperature. An inverse exponential relationship was expected with adsorption plateauing at low temperatures as pores reach capacity. Results? Partial conformation plateauing occurred but at higher temperatures than predicted, suggesting the system didn't reach full capacity. Hypothesis number 4. Experimental validations. Simulated absorption values at around 280 to 300 Kelvin should align with experimental data. Results? Confirmed. From available pressure-dependent studies, but no temperature spectrum comparisons were found. Hypothesis number 5. Pressure effects on entropy. Entropy should increase with pressure. And the results? The hypothesis was incorrect. The higher pressure led to a linear decrease in entropy, except near vacuum conditions where it approached zero. Finally, adsorption versus pressure. Expected inverse exponential trend plateauing at high pressures. Results? The hypothesis was proven once again incorrect, with absorption increasing linearly with pressure in the test low pressure terrain. Further research questions and where to improve. First, we could determine acetaldehyde pureness and find a way to increase the return yield. Then we can determine glycoxyl pureness, how to make the process safer and decrease the risk of fire issues. Third, we can improve the glycoxyl synthesis process to increase yield, improving the 2-methyl-imidazole synthesis process. Then we can find out other purification methods for the 2-methyl-imidazole solutions. We can find the crystallization method that would lower the risk of destroying the compound, yielding close or approximate to pure crystals. Then we can improve the variables during the ZIF 8 synthesis. We can modify the wattage, the volume of the solution, the amount of zinc ions, and the time we can expose it under microwaves. We can also use more accurate equipment that would give us exact wattage, except instead of the microwave we had. Then we have to ask ourselves how good is the synthesized framework. We can determine this using X-ray crystallography, but this equipment is unavailable to us this time. We also have to ask the question, does modifying the ligand of the framework improve its adsorption capabilities? aka how does manipulations of 2-methyl-imidazole impact the final result? What is the optimal way to produce high quantities of ZIF-8? Is it ecologically worth it to produce it? Does the damage of production outweigh the benefits it would yield as capture of CO2? What is the best way of activating the ZIF-8 framework, and investigating whether other MOF synthesis methods would yield better results like evaporative crystallization or sonic chemical. This project took a lot from us. Hundreds of hours spent, tens of pages written, tens of articles read, and liters and upon liters of chemical vapors we breathed in were definitely bad enough to have shortened our lifespans, but at least about a couple of months to maybe a couple of years. But in the end, we managed to synthesize our final product, we proved our hypothesis, or most of them, and even developed professional level data which is credible enough to be included in other papers as a source material. We have to admit that the reactions we conducted weren't the most efficient or professional. However, at our level of education and laboratory environment, we managed to finish a university level project by employing almost exclusively our own knowledge. We have to definitely thank you for watching this video, and we'll see you next year at the science fair. Bye!